Okay, so the last module about isolation is software fault isolation. Now this is a very vibrant area of research today, so we are not going to go into too much details. So what we are going to tell you is a few things about software fault isolation, so you are aware of what the features of this research area is. So now until now we saw that we are trying to confine different processes into different virtual machines or jails or this kind of or in different hardware altogether. Now suppose you have nowadays most of the software has multiple threads, and therefore they are using the same address space. So then the question is, can we do isolation between them, because if one thread is doing something dangerous, the other threads should not be affected, or the other threads might be having certain different privilege level and so on. So therefore we need to isolate them as well. So so for example, let's say you have a media player which has also a codec thread that does coding and decoding, and they do not need to interfere with each other. Device drivers should not corrupt the kernel and so on. So, so simple solution would have been that you run different address space processes, but that will make it very slow, because inter-process communication is lot more work, lot more time consuming than intra-process communication, because it will require context switch. So we want to avoid context switch and keep the advantage of having multiple threads, but at the same time we want to contain damage arising from one thread for the other threads to be affected. So what is done normally is that although you have the same address space, but you divide the address space into segments, and these segments are then used to contain the access of various threads. So the thread 1 or application 1 could only access this first part of the code segment and data segment, and then the second one can do the same thing and so on. And this works for 32-bit address space. It is not so good, but nowadays with 64-bit address space this obviously is quite possible. Now some of the unsafe instructions is normally like when you jump from a particular address in the code segment to another particular address, unless you check that you are not violating the segment and going into the code segment of the other threads segment, then you need to do something. Similarly, load, store and other kind of instructions also have the possibility of loading things in the wrong segment and so on. So therefore you have to locate these instructions. So you basically have to instrument your software. Let us say you are given binary or whatever, and then add these checks so that segments are not violated. So these are called the guards. The guards will basically check that you are not violating anything. So there are two techniques here. One is called the segment matching technique, and the other one is called the address sandboxing technique. So segment matching technique basically does the following, and it was designed for MIPS processors. So they keep two dedicated registers to do the arithmetic for segment addresses, and so DR2 contains the segment ID. So suppose you are trying to load from this address, so this instruction will become this many instructions, because what you have to do is that you have to compare the segment register and DR2, and then if they do not match, then you trap out of this code, otherwise you and do some exception handling, otherwise you know that you are safe because your address that you are loading from is okay. So that means that you are basically adding some overhead in terms of guard code. So, so DR2 in the address sandboxing technique, we want to actually reduce the overhead somewhat. So, what you are going to do is that you actually have a segment ID, and then you take the address that you are trying to load from, you take that and use a segment mask, because you have your own segment, and then you know, match it against the segment ID, and then if it goes through, then you do this. So, then you are getting some fewer instructions here, but in the other one, the segment matching technique, what you were doing is you are trapping when it does not match, and therefore you were actually catching the offending instructions. In this case, you will have to forego that. Now, the other thing is that you have to automate this you know, insertion of these guards, and depending on how good your tool is, you might miss some unsafe instructions, and then your tool will be not so effective. So, then the other question is that suppose you have a jump to an address, and the jumps directly to into an indirect load. Now, remember that where is the indirect load? Let us say now you have this instructions. Now, let us say it jumps directly to this, right. Now, that is not good, because you are basically you know, foregoing the guard. So, the solution of that, you also have to have a guard around the jump, to ensure that the address jump to that address does not bypass the load guard. So, this is a lot of work, and also there may be cross domain calls, like, you know, so in one you want to make a call that to a function that belongs to another. So, for that you have to insert some stubs, and then you have to have a jump table, and you have to actually you know, add a lot of the patch to your binary to do all this, and that obviously is going to affect the performance. So, in summary, you in software fault isolation, what you want to do is that you want to make sure that your address space of the same process is segmented properly, and then you have to make sure that your segmented address is not violated by any of the instructions. For that you have to do instrumentation, and the performance penalty for example for MPEG. So, people have been doing this various techniques, and they are actually also developing benchmarks and their performances. So, for example, this one MPEG play, for that there is a 4% slowdown, so that is not so bad. It is harder to implement on x86, because you have variable length instructions. So, you can actually, you know, making sure where to put the guards is makes difficult. It has fewer registers, so cannot dedicate 3 registers for the fault isolation, and many instructions affect memory. So, more and more guards are needed. So, that brings us to the final slide on isolation. So, we saw that there are many ways to sandbox applications to contain damage. Obviously, physical air gap is the most direct one, but very expensive and not usually done. Virtual air gap, which is through the hypervisors or virtual machine monitors. System call interposition, software fault isolation, and then application specific, for example, JavaScript in browser. When we go to the browser security, we will see a lot of this sandboxing and containment happens within the browser. Often complete isolation is inappropriate, because then you have to also figure out how to do the inter-application communication, and you have to have spatial regulated interfaces. Hardest part of sandboxing is specifying the security policy. So, what can apps do or not do? It is often not very easy to articulate, and also the bigger one, more technological one, is that covert channels do exist between various sandboxes, and that might be more difficult to plug than the other things. So, next we will talk about rootkits.